Hi, my name is Sophia, and this is my week 5 reading. So this week we talked about magnetic fields generated by a single charged particle and by a current of charged particles. For a particle to generate a magnetic field, it must be in motion, and the magnetic field will spin around the particle in a direction perpendicular to the particle's motion. So like if a particle is moving like this, then the magnetic field will just spin around the particle like that. Okay, and more specifically, the direction of the magnetic field is given by the cross product of the vector showing the direction of the particle's motion and the vector from the particle to an observation location. So the vector, the two vectors, the vector giving the direction of motion and the vector towards the observation location, are in the same plane, so technically the cross product vector, i.e. the electric field vector, will be perpendicular to both of them. Okay, and so the direction of the magnetic field also depends on the charge of the particle. The direction of the magnetic field for a positively charged particle will be in the exact opposite direction of the magnetic field for a negatively charged particle. And then after that we discussed a formula for a magnetic field, for deriving the magnetic field of a single charged particle. So the formula basically closely resembles the formula for finding an electric field. Both formulas have a constant of proportionality, and they account for the charge of the particle and the distance from the particle to the observation location. They also have a direction vector. However, the constants of proportionality between the two formulas are a little different. And also, in the electric field equation, the direction vector, just points in the direction towards the observation location, or rather, from the observation location to the particle. And in the magnetic field equation, the direction vector is perpendicular to both the direction of the particle's motion and the direction towards the observation location. Okay, and next we discuss the idea of currents. In a conductor, there are charged particles, positive or negative, though most commonly negative, flowing in a particular direction. And a current is simply a measure of the number of charged particles crossing a particular location over an area, per unit of time. And the particles move in a direction with an average velocity called the drift velocity. Okay, and so in other words, the current is just basically the rate at which the charged particles travel. So we also introduced the idea of conventional current. To calculate conventional current, you have to multiply the rate at which the particles pass a certain location by the charge of those particles. And if the flowing charges are positive, then the direction of the conventional current will be the same as the direction of the drift velocity. But if the charge of the particle is negative, then the direction of the conventional current will be opposite to the direction of the drift velocity, because you're essentially multiplying the particle's motion by a negative sign. And we also discussed how to determine the magnetic field generated by a flowing current. So the magnetic field of all the particles in the current is basically the sum of the magnetic fields generated by each particle. And since the magnetic field generated by each particle will be the same, instead of calculating the magnetic field for each individual particle and then summing them all up, we can just calculate the magnetic field for one particle and then multiply that by the number of total particles in our conductor, or in a piece of the conductor that we're interested in. And after that, we discussed how to calculate the magnetic field generated by particles flowing through a straight wire. So the magnetic field of the whole wire is basically the sum of the magnetic field of all the small pieces in the wire. And to find the magnetic field of one such piece, we basically use the same formula as the one for calculating the magnetic field generated by a current, but we substituted delta L by the length of the piece of the conductor that we're interested in. And if we make the pieces infinitely small, we can use integration to calculate the sum of all the magnetic fields of all those pieces. And finally, we talked about finding the magnetic field generated by current traveling in a wire loop, which uses kind of the same principle, finding the sum of all the currents flowing through each piece. So the thing that I found the most confusing this week is the amount of what seemed like new information. But then, when I decided to go back and rewatch the videos a few times, I realized that the ideas are actually pretty similar to the ideas behind finding an electric field. So, so the calculations are the same and everything. And something that I found pretty interesting was that that there's a distinction between conventional current and electron current. So electron current just measures the rate at which electrons move past a particular point, but for conventional current, you also have to multiply that rate by the sign of by the charge of the particle. And I guess this week's material is relevant to engineering broadly because, lots of engineering devices use some sort of electrical current to work. All right, well, thank you.